Hey guys, Ms. Gosling here. In this video, you are going to learn about diffraction. And this is our HL extension for diffraction. So in the video, by the end of the video, you'll be able to describe and solve problems involving diffraction gratings and thin film interference. So with that, let's go ahead and get started. So the first thing I want to mention is what a diffraction grating is. So a diffraction grating is going to be something in which there are multiple slits that the light can pass through. So we've talked about the single slit, we've talked about the double slit. We could also have 3, 4, 5, 6, 7, 8, 9, 10, a million slits. A million might be a lot. It might be a lot to ask for a small space, but we can have many, many slits that light is passing through. And when we do that, instead of just talking about diffraction, we're going to call that a diffraction grating. So one thing that is really important to know about diffraction gratings is they create sharper and sharper lines the more slits there are. So for example, if we have a single slit, you can see here, this is the diffraction pattern that we will get. So I'll have that sharp peak in the middle and then smaller peaks out to the sides. When we have multiple slits, what we'll get is within each of those peaks, we'll have multiple smaller peaks as drawn in these red lines. So we'll have smaller minima and we'll have many more local minima and maxima. So rather than seeing, for example, something that looks like this with a single slit, what you may see is something that looks like this. These should be 3. I'm having some trouble drawing them. But what you'll see multiple minima and maxima within that single slit envelope of light. The more slits that we have, the more defined those peaks will be. So we have our double slit perhaps as those blue lines. If we were to talk about something with 7 slits, rather than lines that are kind of meshed together, what you'll see is separate dots. Very, very distinct. So what this means is the more slits we have, the clearer each of our separate lines is going to be. So mathematically, when we have light and we send it through a diffraction grating with slit distance d, we are going to see that the angle of each separate maximum is given by n, so the number of the maximum, so 0 for center, 1 for the ones next to the center, 2 for the ones after that, and so on and so forth, times the wavelength of light. And again, that's going to be equal to the slit distance times the sine of the angle of each separate maximum. Now, one thing that's really important to note is that our slit distance is not usually given for diffraction grating. Rather, what we're usually given is the lines per millimeter. And so in order to go from that to little d, what we're going to do is divide 1 by the lines per millimeter to get the distance between our lines, and we can use that to solve our diffraction grating problems. So the next thing I want to talk about is something called thin film interference. So a really good example of thin film interference is light reflected off a soap bubble, which we can see in this image on the left. Now, when we have thin film interference, what will happen is we will see some kind of a rainbow of light, and we'll see the separation of the light by its wavelengths. The reason this happens is that we're going to have an incident ray of light that's going to hit our film. Some of it is going to be reflected, but some of it is going to get refracted through the film, and when it hits the inside of the film, it'll be reflected off of that and refracted back out of the film. So although the angles between our initial reflected light and our refracted and then, or our refracted, then reflected, then refracted light will be the same, because my second beam of light is going to have a farther distance to cross, or distance to travel. We're going to be able to have interference between 1 and 2. One thing to note, I only talked about 2. We can continue having some light get reflected within the film and have multiple different beams of light. So we can have 2, 3, 4, 5, 6 different beams of light that are all interacting with one another. So we're going to have destructive interference when 2 times t, which is the width of the film. So in our picture, this is going to be t, times n, which is, of course, going to be the angle, or the index of refraction for our film. So for our soap bubble, that'll be the index of refraction for soap. And that is going to be equal to m, which is going to be any whole number. So 0, 1, 2, 3, etc. Times, of course, the wave lambda, which of course is the wavelength of light. And again, that is when we're going to have destructive interference between rays 1 and 2. However, when we have m plus 1/2, so when we have kind of a half integer multiplied by our wavelength, if that's equal to 2 times t times the index of refraction for our film, we're going to have constructive interference. So that is the math for thin film interference. And again, these are for our waves that are reflected from the film. Now, because of this interference that we're seeing, we are going to get this lovely rainbow pattern on our thin films. So let's go ahead and talk takeaways. First of all, having more slits results in narrower intensity peaks. So rather than a single broad light, broad beam of light, we'll see smaller dots within that broad spectrum of light with dark spots between them. Next, thin films cause interference, which is what creates that lovely rainbow effect. And they do that because the waves have to travel different path lengths. And finally, the most important takeaway is that thin film interference makes soap bubbles look beautiful. So just a reminder of some of the aesthetics of science and of physics in particular. Okay, so with that, I'm going to go ahead and leave you to solve some of these problems on your own. Best of luck and happy solving.